So far, in prior videos on chemical kinetics, we have defined the rate of chemical reaction, and the way that we have done this is by doing the following. Okay, suppose that you have a reaction A to give B. We have said that the definition of the rate, the instantaneous rate, is going to be equal to the change in concentration of reagents over time with a change in sign to make the rate positive. Something similar could be done with products. Now, something interesting that we have seen as well is that the rate can change as a function of time. Right? So if we're able to plot how the concentration of A changes as a function of time, this can have various forms. It could be perhaps linear, or sometimes it might be exponential, or sometimes it might have some other form. Let's assume for this discussion that the way that it changes is something like that. Okay, that's how A disappears as a function of time. Something that is quite interesting here is that the rate does change as a function of time. And notice how if we were to calculate the rate at that particular point, we would simply need to measure the slope of this tangent line to the curve at that point, and that slope would be exactly this quantity, change the sign, and that will give you the rate. Well, it's pretty obvious that the rate at that point is quite different from the rate at this point. Okay, where if we measure the slope of the tangent line to the curve, then we will find that the rate will be much smaller. Okay, this actually suggests that the rate depends on the concentration of reagents. Right? Notice how when the concentration of reagents is high, the rate seems a little higher, and when the concentration of reagents is a little lower, it looks like the rate is also lower. Okay, so this is actually what the rate law is. The rate law tells you how the rate of a chemical reaction depends on the concentrations of reagents. Okay, so for a reaction like this, the rate law has this form. Rate is going to be equal to proportionality constant K times the concentration of your reagent A to a power that needs to be specified. Okay. All right, so let's talk about this is again the rate law. The rate law tells you the dependence of the rate on the concentration of your reagent. All right, let's talk about this exponent right here, x. A common misconception is to assume that that exponent is related to the stoichiometric coefficient of the reagent in that reaction. But that is actually not true. In principle, you have no idea by looking simply at the reaction whether this number will be 1, 2, 3. There's no way to know this. Sometimes those powers can actually be fractional. Sometimes they will even be negative for some species. Okay? Regardless of what this number happens to be, that's what we call the reaction order. Okay? That's the reaction order. And again, this is something that you cannot determine simply by looking at the reaction. You actually have to do experiments, go to the laboratory, and we will learn how to do this in order to be able to determine exactly what that exponent is. Right, so suppose that this exponent happens to be 1 after you have done a few experiments to determine it. If this exponent is 1, then we would say that the order of the reaction is 1. This will be a first order reaction. Okay? Suppose that you actually do a different reaction and then the exponent, that reaction order happens to be 2. In that case, we will be talking about a second order reaction. Okay? When the number is fractional, then it's a little bit more difficult to say what order that is. You can say order 1.5 or order 1.25 or whatever it is. But again, that is just the reaction order. Okay? This proportionality constant is what we call the rate constant. Okay? That is the rate constant. Okay? And the rate constant again is simply the proportionality between the rate and the concentration of reagents elevated to the power of the order. Now, the rate constant is very important because the temperature enters the rate through the rate constant. Notice that we generally say that chemical reactions tend to go faster when the temperature is a little higher. But if you take a look at this definition of the rate, the temperature is actually nowhere. Okay, well that's because the temperature enters this rate law through the rate constant, and we will actually learn how that happens a little bit down the road. Okay, Something important about the rate constant is that the units of the rate constant depend on the order of the reaction. Okay, so let's try to talk a little bit about that. Let's suppose that the rate, we measure the rate in molar per second. Okay, these units are always the same. They do not change with the order. The rate is always the change in concentration per unit time. So if we use molarity as a measure of concentration and second as a measure of time, then the units will be molar per second. But again, this does not depend on the order. And then let's assume that the order of the reaction happens to be 1, first order reaction. Well, if that's the case, then what we actually have here is the following. The units that we'll have is that, well, if this is molar concentration or molarity to the power of 1, okay, then the units of the rate constant happen to be, or need to be per second. Okay, so that is what will happen for a first order reaction. The units of the rate constant are per second. But let's assume that the reaction order, instead of being 1, let's assume that the reaction order is 2, just for the sake of discussion. Okay, well, the units of the rate are still concentration per unit time. That doesn't change. Okay, now when you take a look at the molarity, the concentration term, then you will have molarity to the power of 2, because this is a second order reaction. That means automatically that the units of the rate constant have to be molar to the -1, second to the -1, in order for all these to yield molar per second. Okay, so again, this is just the definition of what the rate law is. We have talked about the reaction order, a number that needs to be determined experimentally, and then we've talked about this proportionality constant, which is the rate constant, and how the units of the rate constant depend on the reaction order. This will be the case for a reaction that has only one reagent. Okay, we can actually try to move a little bit forward and see what happens when you actually have 2 reagents, and how this can get a little bit more complicated. Okay, so suppose now that your reaction that you're interested in would be A plus B to give, say, C, something like that. Well, the rate law will be defined as follows. You have the proportionality constant, which is the rate constant, and then the concentration of the reagent A to a power that you have to determine, and then the concentration of the other reagent B to a different power, in principle, that you also have to determine. Okay? So here there are various different cases. X and Y can be the same, they can be different, they can be positive, sometimes they can be negative, they can be fractional, they can be anything. Okay, but just to take care of the more common occurrences, it could be quite common that X might be 1 and then Y might be 1. Then what we will say is that if X is equal to 1 and Y is equal to 1, then what we will say is that this reaction is first order with respect to A, first order with respect to B, and second order overall. Okay, the overall reaction order will be X plus Y. This is equal to the overall order of the reaction. Okay, so for this particular case, where the overall reaction order is equal to 2, we'll have an overall second order reaction. Then what we'll have is, when we think about the units, is that the units of the rate will be molar per second. Then we'll have that all of these units will be molar times molar. Okay, so it will be molar squared, and that means that this the unit of this rate constant has to be molar to the -1, second to the -1. Okay, so this is your introduction to the rate law, which again expresses how the rate depends on the concentration of reagents.